morning, everybody. I know the agenda says we're going to have 10 minutes of opening remarks. I haven't got much to say, so we're going to build in a 10-minute buffer before our poster break and get started at 8:30. This morning's session is on mechanisms and predictability. I think it's task team 3, although I usually get the numbers mixed up. It's the same format as we had yesterday, right? We're going to have a few talks, we're going to have posters and break, a few more talks, and then 45 minutes of discussion before lunch. Our first speaker is John Robson, and he's going to talk about mechanisms and predictability of AMOC. So that's right on target.
John, I'll give you a 2-minute warning.
Okay, thank you. Right, can you see my slides? I'll just change the display. Does that look okay?
You might need to change the display again. It reverted back to presenter notes.
Okay. How's that?
Perfect.
All right. Good morning, everyone in the US, I guess, and hello to everyone else in Europe and everywhere else. So yeah, I'm going to talk about some mechanisms and predictability of the AMOC, progress and challenges. So Mike asked me to give a kind of retrospective talk over some of the things we've learned over the last 10 to 15 years, and so I'm going to try and cover that. So thanks very much for the invite to talk. Thanks very much also to the many collaborators over the years, and I've put a few of the names there. And also thanks, to the wider AMOC community who've taught me a lot about the AMOC over the last 10 to 15 years. I'm really sorry I can't be there today. I would have loved to have been there. And it's kind of funny, you kind of thinking about these retrospective talks, you kind of think back how things have gone over the last 10 to 15 years. And in fact, the US AMOC in Miami in 2010 was the first time, my first international meeting, as I just finished my PhD at that point. And one of the things that stuck out to me in there was I got in a bit of a weird argument about HADCM3 of all things. And the argument kind of went along like this, which was, someone with the chair of the breakout session on the mechanisms and predictability group was saying, HADCM3 is rubbish. It has all these different AMOC mechanisms. How can we trust it? And I tried to argue back that, this is exactly what we expect from a complex nonlinear system. But of course, there's lots of things going on. We need to know what the dominant driver is, and this is a bit of a joke on the NAO and stuff. So I spent the rest of the day wishing I hadn't had that argument and feeling silly about myself. But thankfully, I bumped into the chair in the hotel lobby or the elevator later on, and they introduced themselves, Gökhan Danilesoglu from NCAR. So since then, it's all been uphill, hopefully, or maybe not. But we'll see. And so to get into this now, so so what's the motivation? Why do we care about the AMOC mechanisms and predictability? And of course, we know the AMOC is highly variable on a range of timescales from days to millennium, and we see this in different timescales or time series, of AMOC observations. This is just from the rapid array. We see it in models, and we see evidence from paleo as well. The AMOC's been linked to lots of important climate impacts through its impact primarily on the meridional heat transport, and particularly the climate impacts like the impact on SST, but also higher impact stuff like hurricanes, rainfall, etc. We also know the AMOC's expected to weaken significantly in the future due to climate change. And so, if we want to make predictions over the next kind of decade or two, to do that confidently, we really need to understand how and why the AMOC's varying and whether we can predict it. So I said the aim of the talk is to give a broad kind of retrospective of some of the key progress and understanding on mechanisms and also the implications for predictability over the last 10 to 15 years or so. That's way too much stuff to put into a talk, which is hopefully less than 25 minutes. So I'm going to focus primarily on interannual to decadal timescales. I'm going to focus on results for motion and coupled models, just because that's what I know best. I'm going to discuss some implications for predictability rather than too much on the predictability side. And I'm going to outline some important questions and uncertainty. And I'm going to take speaker's prerogative, if that's all right, and where possible, highlight work from UK funded projects, which I've been involved with over the years, Sorry if I don't mention your work. There's no disrespect there. And I guess this is a good opportunity for me to thank NERC over the years, the UK funder, who's put a roof over my head and given me lots of intellectual satisfaction. So let's get into it then. So we know, I think one of the things that we've got more confidence in over the last 10 to 15 years is there are many, many different processes that play a role in AMOC variability. And this is just a summary schematic from Helen Johnson's paper from 2019. So, you know, there's loads of stuff here from heat flux anomalies, eddies, Rossby waves, changes in diapycnal mixing, inter-basin exchange, etc. And there, I guess the key thing is that we know that the dominant processes depend on kind of where you're looking, where in the Atlantic you want to look at the AMOC, but also on the time scale. And I guess broadly speaking, you can separate these kind of mechanisms into kind of intrinsic to the ocean, internal to the ocean, and kind of surface force, so like the ocean's boundary condition change. I'm not going to talk much about the intrinsic variability, and I see that Thierry is talking later, but I think the general summation, or my knowledge, is that, you know, model-based estimates suggest that it's really this surface forced variability that dominates the AMOC on interannual to decadal timescales at least. And this is just an example from a recent paper from Gourmet et al. I think it's just come out, where they launch an ensemble, a small ensemble of 12-degree ocean-only runs, and they see, they basically see that the spread in the ensemble for this kind of 2010 decline in the AMOC is small due to differences in the initial conditions, so the internal part. So one caveat of that is that the model is still not recreating the size of the anomalies that we see in the observations, and I guess that would be a key theme about model uncertainty. If we look at the role of surface forcing, then I guess one of the things that we know much more about is the differing role of wind, so the mechanical wind forcing, which I call wind generally, versus the buoyancy, the role of buoyancy forcing. And really, I guess it's a similar message, which is the importance of those two things depend on where you are and also what timescales. So this is just a schematic from Laura Jackson's review that came out earlier this year. And we kind of made the argument that for this, in the subtropical gyre, wind forcing dominates shorter term variability, up to decadal variability. But in the subpolar gyre and on decadal timescales, it's really the buoyancy forcing which dominates. And there's a whole range of papers that talk about this, and I haven't listed them all here. So if we look at interannual variability, and specifically at the role of wind forcing, we know, especially from the rapid array and many other studies, that we know that the wind is obviously the key driver of the Ekman changes, which plays such an important role on kind of monthly and interannual variability. But the wind is also important for driving the geostrophic variability through a number of mechanisms. And I'm just going to highlight one study here, which is a study that was led by Irene Polo back in 2014. And what we did was we had an ocean-only run, and we had time-varying wind forcing, mechanical wind forcing, but kind of climatological buoyancy forcing. And a couple of mechanisms popped out on the kind of very short timescales, and instantaneously with the AMOC, we saw changes in wind along the western boundary, led to Ekman upwelling on the boundary, and this is heaving the isopignals and driving the geostrophic AMOC in that way. But on slightly longer timescales, on interannual timescales, what we found is that actually the wind forcing plays an important role in kind of initiating Rossby waves in the interior. So you get this Ekman pumping anomaly. This is 16 years before a peak in the AMOC. This kind of initiates a density anomaly, and this propagates west. This is 4 months before. And I think, you know, in terms of AMOC at 26 north, I think, you know, the general understanding is that wind-driven variability is really the dominant driver of this kind of sub-decadal variability at rapid. It may not be true elsewhere. And there's kind of plenty of papers that look at that kind of variability as well. I guess one interesting thing about this wind-forced variability is there's been some interesting kind of implications for predictability, which have been arising. So we know from RAPID and other studies that this interannual AMOC variability does shape upper ocean temperatures, SSTs, and heat content in the North Atlantic. And that changes in the heat transport and heat content has been linked to high impact weather. So this is just a relatively recent paper by Sam Hallam from NOC, where they link variability in the Ekman, changes in rapid to changes in the main development region SST anomalies. So in this case, a weakening of the AMOC due to the Ekman leads to less heat coming out of the tropics and therefore an increase in the SST in the main development region, and therefore maybe implications for hurricanes. One thing to say about this is if this variability is largely wind driven, then it's really the predictability of the atmosphere which is really key to kind of get this AMOC related climate impact, if you like, rather than the ocean. The ocean may play some role, but it's really the atmosphere that's important. But yeah, I'd still make the argument it's really important if you want to get these AMOC related climate impacts. We really need to do a good job of representing the AMOC in its variability and of course its impact. So moving on to the decadal variability, then I guess there's kind of three broad main contenders, and one is changes in buoyancy forcing through changes in surface fluxes of heat and fresh water. There's changes, some studies have highlighted the importance of Rossby waves, and in particular, I guess, what Florian called thermal Rossby waves. They're kind of self-fulfilling, I was going to say, well, there's like a feedback there, which makes them self-replicating, and they continue in time. But of course, because they're occurring at very high latitudes, they propagate west at very slow speeds, and this leads to decadal variability on the western boundary in terms of density. And the last aspect is kind of decadal changes in the wind themselves. So the wind variability has multi-decadal variability in it. And this can lead to, I think what Susan has previously called kind of like Jiayan modes of AMOC change. So you can have an increase in the subpolar gyre, but a decrease in the subtropical gyre because of the impact of the wind. So I think it's fair to say that in terms of decadal variability, it's still that the NAO is kind of thought of as the primary hypothesis, if you like, for forcing decadal buoyancy forced variability in the AMOC. And I think most of that evidence comes from ocean-only simulations, actually. So this is a result from Zhang in 2019, where he looked at ocean-only runs, all forced with the core surface forcing data set. And you see this strong and robust correlation between what the NAO is doing and then the AMOC later, about a decade later. We know from other ocean-only simulations, which have kind of decoupled the wind and the buoyancy force runs, that this AMOC changes at the high latitudes that we see in the ocean-only runs is driven by the changes in buoyancy forcing. And you can see similar things in coupled models too. So this is just an example from Delworth and Feng, but where they add additional heat flux or heat loss in this case to the coupled model, and they see a spin up of the AMOC kind of 10 years later or so. So that's kind of one of the dominant paradigms, especially from ocean-only runs. But of course, it's not that simple. In particular, in coupled runs, there's a much kind of broader set of mechanisms. And one of the key things is to say in coupled runs, so this is the same analysis from Xiaobo's analysis, but with coupled runs, you see that there's a much bigger spread in the response, or the expected response between NAO and AMOC in CMIT5 runs. Some do have a strong response, and some have a much weaker response. And there's also a much bigger, well, I've called it a menagerie here, of buoyancy force variability. And I can't talk about all of the different mechanisms because there's a huge array of them. But some models, you see a large role for the Arctic, changes in freshwater export out of the Arctic, especially down the East Greenland Current. Some other models, you see a big response, a bigger coupling between the AMOC, the meridional heat transport, and changes in the ITCZ, which lead to changes in the precipitation in the tropical and subtropical salinity, which propagate north into the North Atlantic. And there are many other mechanisms, including variability in the Agulhas current and all sorts of things like that. And I guess we still have this problem in runs, in models, that we have this large spread, and a good example of how sensitive models can be about this is this recent paper by my PhD student Michael Lai, where he analysed it was A and V and AMOC relationships in the latest UK models. And if you look in different models at different resolutions, so this is kind of a medium resolution with a 1/4 degree ocean, and this model's one with a 1 degree ocean, you find different dominant mechanisms basically. So in this model, it's got much tighter coupling to what's going on with the NAO. You even see a reversal of the NAO after peak AMOC. Whereas in the low resolution model, there's some sort of not quite NAO-like atmospheric variability, but actually what dominates, and I'm not showing it here, is kind of freshwater transport out of the Arctic, which gives the similar AMOC variability. And in fact, they have very similar frequency variability in terms of their AMOC, but they're just driven by different mechanisms. If you're interested in the NAO-AMOC relationship, then please see Annika's poster in the break, where she's been looking at the CNRS-IGE. Now, in terms of, although there's a very broad array of physical mechanisms for how the buoyancy forcing change, one of the key things which is important for AMOC mechanisms in ocean and coupled models is that once you get density or thickness anomalies into the subsurface, then that can affect the AMOC across the whole basin, basically, in the models. And so a couple of examples of this, Pablo Ortega had a recent paper where we looked in coupled models in CMIT5, and basically this is the relationship between subsurface density in the western subpolar gyre versus AMOC at 45 north, and there's quite a tight relationship there on well, kind of decadal timescales. These are actual correlations in trends, 10-year trends. And this persists in all of the models down to 26 north, but this relationship is weaker and much more uncertain about how strong it should be and what the dominant timescales are. And I guess there's part of that is there's, again, lots of different processes by which those density anomalies can move southward in the North Atlantic. So, for example, some models, the density anomalies in this western subpolar gyre are a key predictor of the AMOC further south because you get these coastally tracked waves. Some models you see advection down the western boundary kind of with the advection timescale, and in some models, like this paper from Steve, you see the density anomalies propagate south in the interior and then interact with the mid-Atlantic ridge, which kind of drives the THC response in the upper ocean and kind of persistent heat transport anomalies. So in terms of predictability, it's true that there's still been relatively little work on AMOC prediction, but there's been some, and in particular, I guess Steve had this paper in recent years looking at the predictability of the AMOC and how sensitive it is at different timescales to whether you're looking in depth space or density space. And I think one of the reasons is that this hasn't been looked at that much is that the skill is really sensitive to model drifts. So that's the mean state drifts, but also drifts in how different variability affects the density anomalies. And Matt Menery's got some interesting papers on that. And I guess one of the key things is it's the initialization of these subsurface density anomalies, which has been really key for giving skill for other things, maybe not AMOC, but for upper ocean temperature anomalies, for example. And kind of this is from Steve's paper, some analysis that Steve did, where he argues that you initialize the Labrador sea density, this propagates south and gives you predictability in the Grand Banks, and this leads to persistent heat transport changes and changes in the SST. And you can kind of see this impact of the subsurface density on the mid-Atlantic ridge in these plots here. So you see persistent upper limb predictability in CSM1. So we also have to touch on external forcings. So it's not just kind of internal variability, there's like an externally forced part to AMOC changes. And I think there's been an increasing realization that external forcings can really affect the AMOC on lots of different timescales too, not just long-term change. And it's not just the greenhouse gases, but it's changes in the solar, the volcanic and the anthropogenic aerosols in particular can lead to short-term interannual to multi-decadal change increases in the AMOC, I guess. And one thing I'd like to highlight is, I'm sure many of you know, but in the latest coupled simulations made for CMIP6, these models now simulate an increase in the AMOC, in the multi-model mean AMOC, up to about 1985 or so, which hasn't been present in these kind of historical simulations before. And that's essentially because the strength of the aerosol forcing is got stronger in many of these models. And so the aerosol is cancelling out the greenhouse gas forced weakening. So that was my uber quick summation of some of the key kind of mechanisms and what we've learned. And so I want to spend a bit of time now on the ongoing questions and challenges. And I guess the point is there are many, you know, Gökhan said yesterday, this isn't a job that's done, and there are many kind of questions we still have, especially on decadal timescales. And you know, one of the main problems is it's still a huge challenge to constrain the details of buoyancy force variability in the North Atlantic. So this figure in the top right just shows, I won't go into in detail, but it's water mass transformation anomalies at different density classes, leading and lagging the AMOC in some different models. Doesn't really matter on the details, but you see that the details of the relationship is different between the different models in terms of where these anomalies occur, how strong they are, and where they're occurring in space, kind of in terms of the Labrador Sea or the Oceanography Sea. And this is another paper recently. So Alex McGann had a paper came out last year where actually they're arguing that in their ocean-only runs, it's really the Oceanography Sea in terms of surface density flux, which actually dominates the decadal variability, rather than the Labrador Sea, which some other models have kind of implicated in the past. We still don't really understand the role of buoyancy forcing, deconvection, dense water formation, and AMOC. And in fact, many previous studies have kind of implicated deconvection changes in AMOC, but we're not really sure whether the models are completely wrong there or whether that's just the wrong interpretation. And we still don't fully understand the role of surface fluxes versus surface density anomalies. So Susan mentioned Tillis's interesting paper and looking at low observations, and we broadly see the same thing basically on decadal timescales in some models. It's not, we haven't looked at all models, but so this is the water mass transformation for these models, which are just due to the surface density changes and again holding buoyancy forcing surface fluxes at climatology. You see most of this variability is recaptured, if you like. If you're interested in the consistency of the response to NAO heat fluxes, then please see Hukin's poster on this in the break. And coming back to kind of what we were talking about earlier at the start, I think, you know, one of the problems, if I can take this sidestep, is that, you know, this buoyancy force variability, in fact, you know, all AMOC variability and the AMOC itself is an emergent phenomena. And the buoyancy force decadal variability is related, as we know, consistently to the densification of water in the North Atlantic. But many different processes drive this densification or water mass transformation, if you want to put it that way. And the representation of those processes, the mean state, and how they all interact are all kind of important for saying that. And it's not just the ocean, it's the atmosphere, where the atmospheric variability is, where the jet bias is, but also the sea ice, which is also an emergent property of the system. So, you know, should we really be surprised that models simulate such a broad range of mechanisms and timescales, and even within the same model, to go back to that Hadsian-free reference? This might be the understatement of the day, but we know that models are not perfect. They have several issues. I'm not going to go through all of these in detail, but we know that ocean models produce too much, or many ocean models produce too much water in the Labrador Sea, dense water, I mean. We know that the AMOC variability is underrepresented in many coupled models. We know there's important biases, again, which affect the variability in the ocean, in key areas in the ocean, but also in the atmosphere. There's too little decadal variability in the NEO, there's jet biases, etc. And I think what this all adds up to is we're still not really sure about the relative roles of different processes and mechanisms. You know, are the ocean-only models overdoing the buoyancy force mechanisms? Are they underdoing the wind force mechanisms, etc.? And there's, and I'll only briefly touch on this, but there are many questions on the externally forced change. And again, I'm not going to go into them much, but I guess one of the obvious problems at the moment is we have a mismatch between the AMOC that's simulated and those that are implied by the historical observations or the kind of proxies. And it's an ongoing debate about what those proxies mean. And there's lots of other questions, including, you know, we don't really understand the aerosol force mechanism and whether it's realistic. And loads of other questions, including, you know, we don't understand the rate of future change. And there's a big spread in models. So if you're interested more on the role of anthropogenic aerosols, then please come and talk to me in the break in my poster, or Michael and I, who's got some some work on some more idealized work. And I guess my overall feeling is that the aerosol force mechanism is probably overdone at present, but we can have a chat about that. So how to move forward? I think, you know, it's obvious we need the low resolution models have lots of drawbacks. These are at least partially resolved by going to higher resolution coupled models, and we've seen some studies showing improvements already. It's important to say that we only have, there's very few very long coupled model simulations, and they're not very well, broadly speaking, the high resolution coupled models are not very well evaluated or understood yet. If you want to see some work that Thierry has been doing on high resolution modeling and how it doesn't solve all your problems, then talk to her in the break. We obviously need to continue to evaluate and constrain the short-term AMOC variability, especially for kind of understanding these AMOC-related risks, where the AMOC may be playing a part in. We clearly need to do a better job in constraining decadal buoyancy forcing and the related mechanism, and we need to think of ways, new tools maybe, more constrained simulations perhaps, or targeted experiments to really try and make progress about understanding the difference between models. And we also need to analyze multiple models where possible and look for observed constraints. On a technical side, especially for me, you know, we kind of need to find consistent and easy to apply analysis tools of key diagnostics. And that goes to what we were talking about yesterday about, you know, deploying the arrays in the models, but it's just about, at the very least, we need to compare the models in a consistent way, and that's not always done. And I think, you know, thinking back over the last 10 to 15 years and you know, the entirety of my career, you know, these collaborative research programs or fora to bring these wide group of people together have been really important, and it would be good if these kind of things continue in the future. So just some conclusions. So we know the AMOC varies on a range of timescales. I won't go through all of this in a sense of time, but we know that the wind forcings may be playing an important role on interannual timescales, and buoyancy forcing may be more on decadal timescales. But there's still lots of questions. We still don't fully understand the relative importance of different mechanisms, even of buoyancy force mechanisms. How do we constrain that? And how are we sure that models respond to external forcing in the right way? So that's it. Thank you very much.
I think we have time for one, maybe two questions for John.
Joe LeCase from Oslo. Just a question about the contribution from the different forcing mechanisms. I guess that also varies with latitude, doesn't it? So if you have, I'm thinking, you know, if you're at lower latitudes, 26 north, where the WHOI may be more coherent, high latitudes where the WHOI are unstable, breaking up into eddies, and maybe at nearer the equator where it's different as well. Is that right?
Yeah, of course. I mean, yeah, sorry if that didn't come over, but yeah, that's really the important thing, is the relative importance of different mechanisms changes with latitudes. Yeah, so that's really what and we're still not really sure about how relative those different, how relatively important those different mechanisms are at different altitudes. But yeah, I agree.
This is Tom Rossby. Given the lack of meridional coherence on interannual, maybe out to decadal timescales, wouldn't it make sense when you talk about AMOC variability to always specify where you are when you talk about that variability? Because the variability of the AMOC is quite different at higher latitudes and lower latitudes. So on your slide here, you say AMOC is in the singular, but AMOC is in a sense really rather plural.
Yeah, I completely agree. I mean, in my defense for this this is my one slide of conclusion, so I didn't want to, have too many qualifying words on it. But absolutely, we can't just talk about AMOC as being one thing, especially on, interannual or even decadal or even potentially multi-decadal timescales. So, you have to be really specific about what aspect of AMOC you're talking about. And that's because AMOC, AMOC isn't just a single thing. Like I said, it's all these different processes, all these different currents and aspects, which can vary differently. Yeah, I completely agree.
Okay, thank you. I think we'll move on to the next talk. Rong Zhang is going to talk about connections between the Arctic and the subpolar Atlantic.
Can you see my slides?
Yes.
Okay, thanks, Mike. Sorry I'm not able to join you in person as I'm tied up with teaching and students' general exams. So here I'll briefly highlight the result from our recent paper on the long-term mean AMOC structure. I thank Matthew Thomas, an UCA associated scientist hosted by GFDL for working with me in analyzing the experiment used in this study. So first, I'll give you some brief background introduction. I also mentioned earlier, CMIP6 model exhibit large spread and uncertainty in the mean state AMOC and the projections of future AMOC changes, causing large uncertainties for projected future regional climate changes. In general, models with larger mean state AMOC tend to have larger future AMOC decline. And the mean state AMOC strength from the CMIP6 high-res MIP historical simulation also has large spread, and also it's sensitive to the modeled mean state deep mixed volume in the Labrador Sea and Jin Sea deep convection region. And it's often viewed that the Greenland Sea is the northern terminus of the AMOC, and the Greenland Sea deep convection provides the densest salt water to the AMOC, although this view has been questioned by earlier observational analysis. There is no established long-term mean state of directly observed AMOC over the past several decades to determine the source of the mean AMOC and whether model simulated AMOC mean state and changes are reliable. And many climate models simulate a strong contribution of Labrador Sea deep convection to the AMOC, but this has also been challenged by observational analysis. For example, as Susan discussed yesterday, recent observations from the OSNAP team during a period of strong Labrador Sea deep convection shows that the AMOC across the OSNAP section is dominated by the east component, and the west component across Labrador Sea is very small. And as the question posted by Susan, it's unclear whether this recent observation represents a long-term feature. So to address these issues in this very recent study, I conducted robust diagnostic calculations using an ID-permitting coupled model GFDL CM 2.5, constrained by the observed hydrographic climatology to provide a holistic picture of the long-term mean AMOC across the Arctic Atlantic Gateway and the subpolar North Atlantic over the past several decades. The RDC method was originally proposed by Sarmiento and Bryan, in which modeled temperature and salinity are restored back to the observed hydrographic fields to produce dynamically consistent fields, velocity fields. And the RDC approach can provide more insight on ocean dynamics, such as the mechanism of Gulf Stream separation and its linkage with the AMOC. So here, the RDC is applied to understand the long-term mean AMOC structure, which can be compared with the same fully coupled model control simulation without any observational constraint. The long-term mean sea surface height in the RDC compares well with the independent satellite observation, the observed mean dynamic topography, with a realistic Gulf Stream separation and a realistic North Atlantic current pathway moving to the northwest corner. And the control simulation exhibits typical deficiencies in the Gulf Stream separation and the North Atlantic pathways as found in many climate models. And the RDC reveals that the relatively denser part of the mean Greenland Skyline Ridge overflow is basically mainly dominated by the deep branch of the AMOC across the Front Strait and Barents Sea opening, that is the Arctic outflow, indicating the densification along the Atlantic inflow entering to the Arctic and the transformed Arctic outflow are important AMOC processes. And in the RDC, the region, including the Greenland Sea, contributes negligibly to the southward downstream mean AMOC transport, despite the presence of strong Greenland Sea deep convection there. And the less denser part of the mean Greenland Skyline Ridge overflow is mainly supplied from the region south of 68 degrees north, where there is no deep convection. And in the control simulation, the deep AMOC branch across the Front Strait Barents Sea opening also provides the densest southward to the AMOC. But the AMOC across all Arctic Atlantic gateways shift to lower densities, which is related to the model's deficiency in simulating the Arctic densification processes. And in the control simulation, the region, including the Greenland Sea, has a barest larger contribution to the density space AMOC across 68 degrees north due to model biases, despite the lack of modeled Greenland Sea deep convection. The RDC estimated mean AMOC across OSNAP is also dominated by the east, not the west component in both the density and depth space, and suggesting a minimum role of the Labrador Sea deep convection in the long-term mean AMOC. And the recent OSNAP observation is not just a short-term phenomenon. And the control simulation shows similar results, but the simulated AMOC across OSNAP East and OSNAP is shallower and shift to lower densities due to model biases. Here, the right panel shows the velocity and density across OSNAP section in observation, RDC, and control simulation. Across the OSNAP East, the density contrast is much larger than that across OSNAP West, sustaining a much larger depth space AMOC than that across OSNAP West through the thermal wind relationship. The control simulation has unrealistically strong Labrador Sea deep convection, but simulates a similar small density contrast between the boundary inflow and outflow, and thus a similar small AMOC across OSNAP West. And across OSNAP East, the latter branch of the northeastern topology area moves northward in the interior and northeastern side above this sloping isopeak at which the maximum AMOC occurs. Meanwhile, the denser branch of the topology area moves southward near the western boundary below this isopeak, resulting in a much larger maximum AMOC in density space than that in depth space. So the horizontal gyre across sloping isopeak contributes substantially, actually more than 40% of the long-term mean maximum AMOC in density space across OSNAP East, providing an additional mechanism for why AMOC is much larger in the east than that in the west in density space. So the much larger density contrast across OSNAP East sustained a much larger maximum density space AMOC through both the thermal wind relationship contribution and horizontal gyre contribution. Previous studies often project AMOC transport onto the TS diagram. I think it's also useful to project AMOC transport onto a sigma Z diagram to illustrate the horizontal gyre contribution to density space AMOC. So here is an example of the sigma Z diagram across OSNAP East. The color shading represents the integrated volume transport over each density bin and depth bin across a section. And the across OSNAP is the positive inflow and negative outflow of the horizontal gyre are partially cancelled along the same depth level, but not along the density level due to their different densities. And the sigma z diagram for observation and RTC are very similar. And the modeled horizontal GR contribution to the density space AMOC shift to lower densities. In the control simulation, the low frequency anomalies of the maximum density space AMOC across the entire OSNAP section, the black line here, are highly correlated with the component across the OSNAP East, which is the orange line here, and also highly correlated with its horizontal GR contribution across OSNAP East, the green line here. And finally, across the entire OSNAP section, the recent observed OSNAP strength over the period of 2014-2018 is similar to the RDC estimated long-term mean AMOC strength over the past several decades. And if you compare to the earlier science paper in 2019, the OSNAP, updated OSNAP AMOC strength, the increase is mainly due to the improved method for analyzing the observed data, including how to deal with lost instrument in the first 2 years. So we can tell that the most recent AMOC strength is close to its long-term climatology. Okay, in summary, the RDC results suggest that in contrast to the traditional view, the deep AMOC branch across the From Strait and Barents Sea opening section, the Arctic outflow, provides the densest salt water to the mean AMOC, and the Arctic Ocean, not the Greenland Sea, is the northern terminus of the mean AMOC. Open ocean deep convection in either the Greenland or the Labrador Sea contributes minimally to the mean AMOC strength. And horizontal GR circulation across sloping espignals contributes substantially to the mean northeastern subpolar AMOC. Actually, the horizontal GR in the Nordic Sea also contribute to the AMOC across Arctic Atlantic gateways, which I don't have time to talk. And climate models need to simulate realistic boundary currents and boundary current density contrast to avoid overprojection of the role of open ocean deep convection in future AMOC changes. And climate models need to have a better representation of the Arctic shelf dense water formation, which affects the Arctic halocline and the density of the Arctic outflow. Okay, I'll stop here. Thank you for your attention.
Questions? I see Gokhan.
Hi, Rong. This is Gokhan. So I had a quick question. If I'm not mistaken, RDC approach requires interior TNS restoring. Is that correct?
Yes, that is the method I introduced originally.
Right.
It's need to restore temperature salinity in the temperature salinity equation, but the velocity equation is not affected.
Right. So as such, I mean, I don't know what you use for the piston velocity, and it's going to change as a function of vertical resolution. But in that case, RDC approach is a diabatic approach. In other words, it creates sources and sinks of energy, sources and sinks of fresh water. So what is the, I guess, what are the impacts of those diabatic processes that are artificially introduced in the system in your conclusions?
Yeah, so first it's introduced diabatic effect, just like data simulation, also introduced those effects. And also, I have very strong restoring 5 days time scale. So you can. I also did overriding experiment. You can just override temperature salinity without restoring. I got essentially the same result. So it's just like observational people when they take hydrographic data, they calculate through the thermal wind relationship. They got the vertical shear of velocity, and then they reference to satellite observation. From the surface to get the surface velocity, but here the RDC, the fully coupled model, give you the sea surface height, so I don't need satellite data. And then the density, temperature, salinity from observation give me this vertical shear. So I essentially it's the same approach from the observation to get the AMOC from a single section.
Hi, Rong. This is Susan Lozier. I appreciated your talk. I did have a comment, though. You mentioned that the horizontal gyre in the subpolar North Atlantic is contributing to the overturning in density space. You know, in the observations, what we've talked about, the importance of computing the overturning in density space, because in depth space, the horizontal gyre is what's keeping that AMOC much reduced. In other words, if you compute it in depth space, the AMOC is much smaller than in density space. And in the observations, what we find is really we can explain the overturning in density space entirely due to surface transformation in, you know, in OSNAP East, which is dominating. So I'm happy to follow up with you, but the horizontal gyre circulation is why we don't want, crossing those isopignals is why you don't want to calculate the AMOC in depth space. It's not a contributor to the overturning. And so maybe there's just, we have a sort of a different interpretation there, but I'm happy to follow up with you later.
Yeah, so here we define the horizontal gyre contribution. Just take the maximum, the difference between the maximum in density space and the maximum in depth space. So that's how we define that. Yeah.
Oh, I understand. Yeah, I think we're saying the same thing, if that's how you're defining it. Yeah, understood.
Right. Right. Yeah.
Over.
Maybe my question is also related to that. So your statement that this is related to the transport across sloping isopignals, that's kind of a diagnostic statement, right? I mean, that implies a lot of mixing, and I was wondering what are the processes that lead to these water mass transformations? And Susan said that it's mostly caused by surface buoyancy forcing. Then it has to translate downward, right? In order for these shallow water masses to transform to deep overflow type water masses. Can you comment on that?
Sure. Yeah. So here, this schematic diagram, the color actually represents the density. So as the horizontal gyre moving across the density, as isopignal is lost heat, you know, along the pathways. So essentially, it's the surface heat loss basically give you the transformation, and then the gyre across isopignal along this horizontal circulation. The transformation just happened along the pathways. In addition to the transformation in the vertical space, in the high latitude, including the current into the Arctic, the horizontal circulation play an important role in the water mass transformation. It's just the surface buoyancy lose, the heat loss interact with directly with the surface current. Yeah.
Okay, we've got an online question from Bill Johns.
Hi, Rong. This is Bill. How are you? I have a question. It kind of follows on from Gokhan's question about some of the impacts of the RDC on diapical processes, and one of those that comes to mind for me is the entrainment process of ambient waters into the overflows. I was just curious whether you think or had any analysis on or thoughts on how much that's been improved.
Yeah. Right. So so the if you look at the difference between OSNAP East and Greenland-Scotland Ridge, between these two sections, this region contributes about 10 spheroidal, water mass transformation. About half is due to the entrainment. Another half is due to this horizontal gyre transformation.
Okay, I think we'll move on to our next speaker. Jiayan Yang is going to talk about topographic influences on AMOC variability.
Okay, well, today I'm going to talk about some topography effect on the AMOC. There's no microphone, okay, sorry. And this project is funded by NOAA. Okay, thank you. Well, AMOC, like any large-scale ocean dynamic system, circulation system, is mostly governed by the geography, okay, away from the friction boundary layer. And in terms of potential vorticities, any large-scale circulation would be influenced by either barotropic or baroclinic, would be influenced by topographies, because topographies influence the potential vorticity distribution. So my motivation is to use a very idealized model and to try to understand some of the observed variability and how topography might have contributed to the observed variabilities. So the approach I'm using is a 3-layer adiabatic model. It's purely wind-driven, so there's no any mass transformation between layers. So that's one way. So the model is very idealized, but I use realistic bathymetries. I set the minimum depth to be 5 meters, so anything, so I don't really have beach. Okay, I have a 5-meter wall along the boundaries. And I use ERA5 wind stress to drive the model. So that's very different from other type of idealized modeling, like what Max Paul is doing, is using a very sophisticated model, but with the idealized forcing and bathymetries. So we are looking at different angles, so the first thing I want to do is to see if I use a very simple model and I just plot the wind, with the results being consistent with observations. And one of the fields that you can most variable to verify that would be the bottom pressure, right? Because the bottom pressure, in a sense, is a geotropic stream function. Not really, because F is a function, but almost like a bottom geotropic stream function. So what I'm comparing here is I'm trying to understand what the bottom pressure would be associated with 2010 AMOC reductions. Those are from the rapid data. The thin line is monthly anomaly, and the thick line is 3 months rounding mean. So I just plot the wind and just look at the result. And the model doesn't really have much degree of freedom, so there's not many things you can tune. The viscosity is one thing you can tune, the bottom drag, and delta rho, and nothing else, because it's just so simple. And the top panel is the bottom pressure anomaly from GRACE satellite observation from 2008 to 2011. So that covered 2009 and 2010 AMOC reduction. And the middle panel is from GRACE. Not from GRACE, from ECHO4 analysis. The top panel is from GRACE. And the bottom panel is from my layer model, my very simple model. And you can see that the model, despite its simplicity, is doing quite good job in terms of simulated bottom pressure. That gives me a little bit confidence that the model might actually can be used to understand some of the dynamics. The signal cycle is even better, but compared with the signal cycle, it's almost like cheating, because signal cycle is so easy to simulate. So if you include signal cycle, it looks much better. Okay. So the top panel I already showed you, that is from the one with the realistic topography. Then I remove all the topography features. I still keep the shape of the coastline. I set everywhere H equal to 5,000 meters. I plot the same wind, same condition, same model. And the bottom panel shows, the lower panel shows the bottom pressure anomaly with the bottom, with the flat bottoms. And you can see that the shape and the magnitude is very different. And that is easy to understand, because the oceans respond to external forcing. It's a propagation of, away from boundary, it's a propagation of Rossby wave. With a flat bottom, it would be planetary Rossby wave, that long planetary Rossby wave that would just go zonally toward the west coast, right? With the bottom pressure, that it will propagate along FOH contours. So that would be strongly influenced by continental slope and mid-ocean ridge. And that is in terms of propagation pathway. But also the magnitude is much larger when you remove the topography, right? So So you can see the amplitude of the bottom pressure anomaly is much larger, and that is very easy to understand too. The reason is the ocean's response to external force in the wind stress forcing is that instantaneous. The Schwarzschild relationship is that instantaneous barotropic response, and it's governed by the Schwarzschild relationship. With the flat bottom, then the beta would be the planetary beta, and in the high latitude, planetary beta is tiny. Okay, so for the same wind stress forcing, the high latitude response will be bigger. But with the topography, typically topography beta, so the response would be governed by the topography Schwarzschild relationship. And topography beta is typically much larger than the planetary beta. Okay, so you can see the response is a little bit different. And also planetary beta, for the same gradient of the topography, planetary beta actually increased with the latitude instead of decreased with the latitude. So both the shape and the magnitude of response are strongly influenced by the symmetry. Okay, that's a very broad overview. Say I do something very dramatic that just remove all the topography features. So now let's go back to the observations. So let's look at the rapid line first. Okay, so from the rapid array, they provide the transport for the 3 layers. So the top panel would be the net overturnings. So I remove the trend, and I also remove the signal cycle. Because again, with the signal cycle, everything looks too good. So I just remove the signal cycle, and I want to focus on the interannual variability. And the middle panel would be the middle level, would be upper North Atlantic deep water transport. And the bottom panel is the monthly anomaly of the lower layer transport anomaly. So what you see is quite interesting is that most of the interannual variability in the lower limb of the AMOC is confined in the bottom layer, not in the middle layer. Okay? And it's not very obvious why. I mean, you would think about if the AMOC is wind-driven, right? It's a wind-driven, the interannual variability here, time scale is wind-driven. Then you would feel like that the middle layer might be more responsive, to wind-driven because it directly feels like the convergence and divergence vortex stretching due to the upper layers. But why would be the lower layer response is much larger? So I put a hypothesis out that it probably has something to do with the topography. Okay, so here's my model control run. I run the model. Again, there's not many degree of freedom I can change in the model. I can change the viscosity, bottom drag. It doesn't affect much. Okay, and the red line is for my model. So I configured my model into 3 layers so I can have a direct comparison with the rapid observations. Again, the thin line is monthly anomaly, and the thin line is 3 month rounding mean, and the black line is from data from the observation. It's doing pretty good job, the model. I mean, but more importantly is you can see the intensification of the interannual variability in the lower limb. It's mostly confined in the bottom layer. Okay, it's mostly confined in the bottom layer. So I decided to look at the AMOC transport in the model that I showed you before, that I just removed all the topographies. And I still brought the same wind. And I still can calculate the AMOC transport in 3 layers. Okay, here's the comparison. So you can see the amplitude of the AMOC interannual variability has been reduced. That's number one. So amplitude, you can see like 2010, amplitude is much smaller compared with the observations. And also, the bottom layer and the middle layer in the annual variability is quite comparable, the amplitude of interannual variability, right? So that gives me some kind of, that kind of support my original hypothesis that topography might have something to do. Then with this model, because it's so simple, so the dynamics is actually quite transparent, that you can play around, try to isolate the mechanism. To make long story short, it's quite complicated. So it's both the mid-ocean ridge and the continental slope play some important roles. And I don't have time to show those. So, but if you're interested, we can talk about during the break. So I did a number of experiments I isolate the forcing or change the topography. So the main topography feature is mid-ocean ridge and the continental slope. So I can just take one away and just look at how ocean responds, adjustment, the topography loss speed wave and how to respond to the external forcing. And the conclusion is both of them matters. Both of them make contributions. For the mid-ocean ridge, there's a one very nice work by Marilena actually about 10 years ago, about the wind stress forcing to the east of the mid-ocean ridge. And the oceans respond originally is barotropic, and when the signal propagating over the mid-ocean ridge, then the response would be undergoing some kind of modal decomposition into the barochanic mode. And that's changed the original local response, which is beginning barotropic. And the continental slope, for the case on the left-hand side, it's also changed the ocean response, which I'm going to talk a little bit. But before I talk about that, I also compare the model with the OSNAP. So the black line is from the 4 years data from the OSNAP. The blue line is from the ECHO. ECHO stopped at December 2017, so for the first 3 years. And the red line is for my model. It's hard to say. I mean, hard to say whether the model is doing a good job or not because the record is only 4 years, and I'm trying to compare with the interannual variability. But overall, at least the signal cycle is quite consistent. Then I compare with the longer record with the ECHO, because ECHO 4 have 26 years. So I just compare with the ECHO over the 4 different latitudes. So the black line is from ECHO, the overturning diagnosis from ECHO from the 4 different latitudes, and the red line is from the model. So it's broadly quite consistent with the model. And the mechanism for the wind stress, how the wind stress for the overturning it can be explained by this diagram. This is the figure from my 2015 paper, which I used to explain the signal variability of the AMOC transport. It's basically due to the wind stress convergence and divergence in kind of adiabatic dynamic system. So you can consider that if there's a polar gyre have anomalous convergence, right, then it will squeeze the lower layer, and that will induce the anomalous southward flow in the deep layer and the anomalous north flow in the upper layer. Then if you add those anomalies into the mean overturning, then you get a positive anomalies and vice versa. I think the same mechanism can be used to explain for the interannual variability. Now let's get back to how the continental slope might affect the AMOC. Let's just take one of very extreme case. Let's assume that the ocean have a purely barotropic response. You try to see AMOC, there's nothing more baroclinic than AMOC, right? Because there's deep water formation, there's overturning, there's 2 layers transport in a different directions in a zonally integrated sense. Then let's try to think about if we have an ocean response which is purely barotropic. Say somehow there's a barotropic flow which is over 4,000 meter depth, which is a Q0 in the interior ocean away from the western boundaries, say 4Q0, so it's 1 Q0. You can say Q0 is 1 swatch per 1,000 meters. And I assume that the anomaly initially is barotropic. So the velocity will be uniform, from surface to the bottom. Then in the upper layer, let's assume the upper layer, the isoprenal is at 1,000 meters. Then I will have 1 Q0 going northward. And from the thermocline below, I have a 3 Q0 going southward, right? Then I need to have a return flow, right? I need to have a return flow. And the return flow, assuming is also barotropic, then there would be 4 Q0 for swatch of return flow. And if that is also uniformly distributed into the vertical, then there's no overturning anomalies because in each layer is balanced. Northward transport in the interior is exactly balanced with the southward transport along the western boundary. Well, now let's imagine that we have a continental slope, a very idealized continental slope, say it's 2,000 meters, right? So in the upper layer, I have one swatch going northward. But now, along the western boundary, I need a return flow of force wardrobe, but that will distribute only over the 2,000 meter depth. So what I get the result is there's a net southward transport of one wardrobe along the west in the upper layer, and the opposite net transport in the lower layer, and that is a net overturning anomalies. So that is a very extreme idealized, and you can apply the same concept to the Ekman transport. I mean, it's easy to say, okay, Ekman transport is just transport within the top 50 meters. But if you think about it, Ekman transport is one of the important components of the wardrobe transport. So we can have a wind stress curve, idealized wind stress curve that only have the Ekman transport, but have no geotropic component. Then the wardrobe stream function still have a return flow along the western boundary, right? And that return flows along the western boundary, when you consider how topography changed that western boundary, that boundary current that needed to balance the Ekman transport, that can induce the overturning too. So the response of the Ekman transport is also affected by topography. I'm kind of running out of the time. So very quickly, well, I can skip that. That's about the pathway along the mid-ocean ridge. Couple more slides. So I try to use that model to look at the tide gauge. So I look at the tide gauge because one of the important topics is how open ocean forcing affect the coastal sea level. So I group those tide gauge into the three groups. The top panel is south of the Cape Hatteras. Middle panel is between Cape Hatteras and New York, and the bottom panel is the New England coast. So you can see the trend. So I remove the trend, then I compare. I compare with the model. Model is a reddish line. So you can see the model is doing pretty good job compared with the tide gauge. Here is a 12 months low pass filter, and you can see that even with for the low frequency, the agreement is pretty good, including 2010 to 2015, the sea level rise south of Cape Hatteras. They have received quite a big attention in recent years. So with the model, with such a simple estimate, we can start to look into how the topography might have shaped the coastal sea levels response to open ocean forcing and also for the local forcing. Yeah. And in the model without topography, you can see that the coastal, the comparison with the tide gauge is completely different. So yeah, here's the summary. I'm not going to read the summary, so because I'm running out of time.
All right, any questions? Ms. Paikuch.
Chris Paikuch from WHOI. Thanks, Jiayan. Really interesting. So you were saying that the sensitivity of your model runs to the specification of dissipation and bottom drag is, for AMOC, it's very insensitive. You could play around with those parameters and you get more or less the same result. Is that correct?
For the AMOC transport, for the coastal sea level, it's sensitive to the bottom drag.
Yes. So that was, you anticipate my question, is that coastal sea level obeys largely frictional dynamics on the shelf. So I'm wondering, I'm trying to formulate some question around the relationship between coastal sea level and AMOC,
right?
And what the implication of sea level being sensitive to the specification of frictional parameters and AMOC not, how does that bear on how we understand the relationship between those two things?
Oh, the sensitive to the bottom drag, you mean?
Yeah, the fact that you find...
the bottom drag, the dynamics of the shelf circulation, the bottom drag, I mean, according to Snoddy's model, is basically the pressure gradient balance the bottom drag and the alongshore wind stress forcing, right? So, and Stevens have a very nice diagnosis that the longshore velocity is more or less in geotropic balance. And that will relate to the sea level tilt, right? So if the bottom drag is large, then you don't need that large velocity to come up with the bottom drag to balance the longshore wind stress. And that will directly affect the cross-shore sea level gradient. But the bottom drag I use is the one that Steve length diagnosis from his identified from the observations. In the paper, Ke and I have, we have the comparison with the different bottom drag. So we can increase bottom drag by 5 times or 10 times. So the change will be about 25%. Yeah. So.
Okay. I see it's 9:40, but I think I'm gonna give the online audience a couple questions to ask. I know there's a question online by Alexei Fedorov. Want to unmute yourself and ask?
I have a quick, very quick question. So, the agreement of your model with observations, does it suggest that there is no role of buoyancy forcing over this time frame? It's just everything is just winds.
For the high frequency, like I'm focused on interannual, but if you look at decadal or longer time scale, then the buoyancy forcing will become, because I removed the trend, so I didn't really look at the decadal trend. But for the interannual time scale, I think the wind stress is dominated, yes. But the agreement is really not that just the model is doing wonderful job. If you think about it, the ocean response to wind stress forcing is basically Schwarzschild response. I mean, then the variability is dominated by barotropic and maybe the first and the second baroclinic mode. And if you have a model to get those right, I mean, the barotropic right and the first baroclinic right, and if you don't screw up the wind stress, then the chance is very small that you don't get right answers. Because a lot of variability we see is governed by simple dynamics, and the challenge is how do we really understand those simple dynamics and have apply to interpret the observation.
Thank you.
Okay, and then the final question from Ranellis online.
Hi, really nice presentation. You may have said this, but I was curious, in the 3-layer model, do you apply a zero net transport constraint, like the compensation that's used in the observations? And I was just curious if you did, if the inclusion of topography or flat topography in your model, you know, if that affects the AMOC calculation differently when that zero net transport constraint is or isn't applied.
Well, it's adiabatic model, so the net mean transport is 0. So it's basically a wind-driven model. So there's no water mass transformation from upper layer to lower layer. So in the long-term mean, the net transport is 0. So I'm only looking at the variabilities.
Thank you.
Yeah.
Okay, I think that completes our morning session. We'll have a break now. Have a break now for coffee and virtual poster session. Thank you. All right, everybody, I think we'll get our second half of the morning session underway. We're gonna have 3 15-minute talks, and then we'll have a 45-minute discussion period before the lunch break. Our first speaker is Marilena Oltmanns, and she's talking about freshwater feedbacks between the Arctic and the North Atlantic.
Hello, yeah, thanks for the introduction. So I will talk about feedbacks between the Arctic and the North Atlantic circulation. And in particular, I will talk about a cycle that links the Arctic with the North Atlantic through ice and freshwater exports, and then the North Atlantic back with the Arctic through atmospheric teleconnections. So since it's a cycle, we start somewhere, and here we start with a cold anomaly. You have seen this already several times in this meeting, so here you can see it again. So it's just an SST pattern, and this is its temporal variability. And next we would like to ask, how does it start and how does it evolve? So we take the time derivative. We just take the time derivative of this time series and regress the sea surface temperature on the result. So we obtain a new pattern, which we call transition pattern for now. And we have already talked about this pattern in the talk. So previous studies have often linked this to a wind-driven signal. associated with north-south shifts in the North Atlantic current, and this has been linked more often to a buoyancy-driven pattern because when there is a warm anomaly, it's a positive AMV phase, and it's also linked to a warm northward buoyancy-driven surface flow. But here we just refer to this as a cold anomaly pattern, and this is a transition pattern. And now we would like to take it one step further and take the time derivative again of this pattern, just to make sure we know how to get into this mode. So when we do this, so this was the first pattern, this is the first derivative, and this is now the second derivative. So there's really nothing else involved, just taking the time derivative twice, and we obtain the original pattern back, but in the opposite phase. So when we decompose the sea surface temperature, we can look at the derivatives and solve the differential equations, and we obtain sines and cosines as solutions. So in other words, it's a cycle. And this cycle consists of these two orthogonal modes that we call transition mode or cold anomaly mode, and it's actually most pronounced on decadal timescales when we look at the involved autocorrelations, and it explains over 50% of the subpolar SST variance. So it's a really important cycle in the North Atlantic. But it's actually also an important cycle for the Arctic, because when we look at the associated ocean and atmospheric variables in the Arctic, we see that the warm anomaly mode is associated with a more cyclonic Arctic gyre and an enhanced Arctic ice export. So this is now based on observations, but models show similar patterns. So when we look at the regression of ice concentration on the warm anomaly mode or the negative cold anomaly mode, then we see an enhanced ice concentration on the eastern side of Greenland. And when this transitions into the transition mode, the ice anomaly has propagated. And when this transitions into the cold anomaly, we see a large freshwater anomaly associated with it over the subpolar region, and this is also associated then with a cold anomaly, and it leads to a range of ocean atmosphere feedbacks that have been described by other studies. I'm not going into any details of the different mechanisms that can link the cycle back to its original stage, to the warm anomaly and then back to the cold anomaly. Instead, I would like to focus on the cycle as a whole and ask how coherent and how close and strong is the cycle actually? Can we also go backwards sometime, or are there alternative pathways possible? And how has the cycle evolved over time? And in order to do this, we first transition to polar coordinates because it's a cycle. So we have these two orthogonal modes, and we transition them into a radius that shows how strong the cycle is at any given time, and an angle that shows where in the cycle we are at any given time. And for simplicity, we just focus on the four main stages again, the four stages that I showed you in the beginning. So here you can see a histogram where the length of the bar indicates the frequency of each mode, and the color is the amplitude. So for instance, the warm anomaly mode is the most frequent. It also has the highest autocorrelations, but it's also relatively weak compared to the other modes. And the feedbacks associated with this mode are also relatively weak. So it's easy to get into this mode, but it's relatively difficult to get out of it. And this has some important implications because this is the mode that is associated, or that transitions into the mode, which in turn is associated with an enhanced Arctic ice export. So it's not as easy to get this ice export as, for instance, the other parts of the cycle. And the warm anomaly usually, so when there's a warm anomaly in the subpolar North Atlantic, there's an enhanced sea surface temperature gradient towards the Arctic, and we obtain a more anticyclonic circulation over the North Atlantic and a more cyclonic circulation over the Arctic. So here's an example from SST forced model simulations. This shows the stream function at 500 hectopascal, and we have a more anticyclonic circulation in the North Atlantic region, but at the same time, it's more cyclonic over the Arctic. However, it's also relatively weak, this signal, and in fact, it's not always what happens. So here, in this time series, the blue years are years where everything just worked perfectly, and the cycle transitioned into the next phase as expected, so it worked really well, it was very nice. But the red years are years where we obtained a cold anomaly directly, even though it wasn't its turn. The cycle didn't work. So what happened instead is that we had a relatively warm North Atlantic region, and due to this more anticyclonic circulation, and we also had more seasonal freshening and more runoff. So we had more freshwater already inside the currents, and we didn't actually need the Arctic freshwater release. We already obtained a cold anomaly just because we had more freshwater inside the current that led to more cooling, surface cooling in the subsequent winter. And we obtained a different cold anomaly, a cold anomaly that looks very similar to the one that I showed you in the beginning, but it's not the same. But it's associated with the same feedbacks or even stronger feedbacks. So the cycle just continues with it, and we take a shortcut. So over the recent years, we actually went from the warm anomaly to the cold anomaly directly, and we skipped the steps in between. And this had some interesting implications in the North Atlantic and in the Arctic. So I will start with the North Atlantic. When we look at the variability of the cycle as a whole over time, so the first shows an atmospheric variable and the second one an ocean variable, but it doesn't really matter which variable is chosen as long as it's part of the cycle. And generally we find that for the atmosphere, so this shows the time, and this is the period of the periodicity, and this is for the NAO in winter. And we always find there is an increased, so the color is power. We always find there is an increased power of variability during cold anomaly and the negative transition phases. But over the recent period, we actually had a lot of power, a lot of variability, even though we didn't have a cold anomaly all the time. In fact, we were actually transitioning between warm and cold anomalies really frequently. And this is shown in the second panel. So this was our decadal cycle. So this is the decadal timescale that we had. This was for the cold anomaly pattern, the cycle I showed you in the beginning. But now it is actually on interannual timescales as a result of this, because we skipped the step in the cycle that takes most of the time. And in the Arctic, the opposite has happened. We have reduced variability. So this shows the Arctic Ocean Oscillation Index, which is an indicator of the circulation regime. And red or positive values indicate a more anticyclonic regime, whereas blue values indicate a more cyclonic regime. So we have now been in an anticyclonic regime for a very long time, and this has led to an accumulation of freshwater inside the Arctic that has been observed by a lot of observational campaigns. So since the North Atlantic is sensitive to freshwater, this accumulation can pose a potential threat to the North Atlantic variability, but as long as it's in the Arctic, it's relatively safe there. However, actually, there is another teleconnection that also leads to a more cyclonic circulation over the Arctic, and this is associated with extreme northward shifts of the North Atlantic current, because these can also lead to temperature gradients increased temperature gradients between the subpolar region and the Arctic. And actually, this is one of the feedbacks of the second type of cold anomalies, which leads to slightly stronger feedback. So over the recent years, we actually had a relatively small Arctic Ocean Oscillation Index that followed the strong recent cold anomalies that had a different mechanism. But here I will just not go into this in more detail, but just conclude that the ice and freshwater exports from the Arctic participated in a cycle that connected the North Atlantic with the Arctic, and it was very coherent. But over recent years, the cycle has actually changed, and because of a new mechanism that also leads to cold anomalies, and this interference has led to an acceleration of this cycle in the North Atlantic, but at the same time to a weakening and to an accumulation of freshwater inside the Arctic, because the Arctic freshwater is now not needed anymore to continue in this cycle. The feedbacks are already initiated at an earlier stage. Thank you.
Thank you. Any questions? Fine. All right, I see a question in the audience by Tom Delworth. I'll pass the mic over.
Thank you for the interesting talk. I wonder if you could comment on how the long-term decline in the extent of Arctic sea ice impacts the underlying dynamics of any variability.
Yeah, this is a good question. So I think a lot of the Arctic sea ice decline, it has to do with the transition to Arctic freshwater instead. So the Arctic Ocean has also freshened. So the link from the Arctic to the North Atlantic can occur both to ice and freshwater exports. And I guess that the contribution of ice has declined and the contribution of freshwater has likely increased as a result of the warming that also occurs in the Arctic.
Any other questions? Should we move on to the next speaker?
Okay. Our next speaker is Thierry Penduff, Atmospherically Forced and Ocean-Driven Interannual Variability of AMOC.
Hi, everyone. Can you hear me?
Yes, we can hear you.
All right. Oops. Can you see my screen?
Thank you.
It's really funny sitting in my office.
Yes.
Okay, let's maximize. All right. Hi, everyone. I would like to talk about two components of the interannual variability of the AMOC, the one which is driven by the atmospheric variability, and the one which emerges spontaneously from ocean nonlinearities, the so-called intrinsic variability. So I'm going to talk about the upper cell of the AMOC, the variability of the upper cell AMOC, and considering density coordinates. So this talk is mostly based on the study by Leroux et al. And so I would like to acknowledge the co-authors of this study. So it started a few years ago. We were using the global ocean sea ice NEMO model with different resolutions. I'm going to show 2 degree, 1/4 degree because we get the message there, but we were using also the 1/12 of a degree simulations. Let's consider AMOC interannual variability at the southern end of the Atlantic basin, so 35 south. And let's compare here the AMOC variability you get at those two resolutions when you drive the model with a full range of atmospheric variability, which is taken from a reanalysis typically. So as you can see, the time series share some similarities, but differences as well. It's not surprising. The two models are quite different. In the blue model, 2 degree eddies are parametrized. In the other one, they are permitted, as we say. But maybe more interesting is the difference you get from those two simulations from those two models when you force them with a repeated seasonal cycle in the atmosphere, completely devoid of interannual variability. As you can see here, the blue model, the 2 degree model, barely generates any variability by itself. But the 1/4 degree model, and that's the case for the 1/12 degree as well, generates spontaneously some interannual variability. This is what we call the intrinsic variability, whose variance amounts to about half of the fully forced. So that was pretty interesting. But in fact, the run was more than 300 years long. And what I show here is the full evolution over this period of AMOC Hofmüller diagrams between 35 south and 70 north for various classes of bandpass filtered frequencies, if you wish. So you see some complex signals, quite meridionally coherent, but there are some complex changes in time as to the direction of some propagations, some intermittency of signals within different frequency ranges, and maybe quite surprisingly, some intrinsic variability reaching up to this band, 50 to 90 years. So the question was, all right, such a model at 1/4 degree spontaneously generates this signal. And to show that, we have shut off the interannual variability of the atmosphere. How do the two behave together? The forced variability, which has been talked about today and yesterday quite a few times, but we have two components there. How do they interact, or how do they talk to each other? So this led us to launch the Occiput project. You can find more details over there. And the goal was to disentangle this forced and the chaotic intrinsic variability. So we used we perform a global ocean ensemble simulation, again using NEMO at 1/4 degree. The ensemble comprises 50 members, and we integrated the ensemble between 1960 and 2050. The principle is here. We have a common spin-up. Then we initialize the 50 members by the final state, and then expose the 50 members to the same fully varying forcing based on era interim. And to trigger the growth of the ensemble spread, we used stochastic perturbation within each member that we switched off after 1 year. So we resume the ensemble like this. And so today I'm going to talk about the AMOC, but we've been looking at quite a few other variables. So it's a generic approach. So we first non-linearly detrend the simulations. We compute the AMOC so that we get some kind of time-dependent ensemble PDF, which is characterized by its time-varying ensemble mean. You see the time variability of the ensemble mean in yellow here, and it corresponds to the variability which is common to all members. And since the forcing is what is common to all members, this is the forced, the atmospherically forced variability. The temporal standard deviation, the temporal variance of the yellow line is sigma f squared, is kind of deterministic if you know the forcing. This is how the ocean responds in the 50 cases. And from the ensemble spread, and you see these members deviate, all of them deviate from the common yellow line by their own random or kind of random variability that is associated with the chaotic intrinsic variability, and we associate a variance, sigma c squared, which is random in phase. And by construction, the sum of those two variances give you the total variance, which is just the ensemble mean of the temporal variance within each member. So using these statistics, let's get back to the 30 south antiradial AMOC variability. So this is the latitude of the Samba array, and the quality is not great, so sorry for that, but as you can see, all those gray lines show individual trajectories for all the members. The black line shows the forced signal, so the ensemble mean, and the differences between the two give intrinsic signals. So first of all, let's look at the bottom panel now. You have over all this range, so this is a diagram showing a nonlinear STD scale and a linear variance scale, but they are equivalent. You choose the one, you pick the one you prefer. But this is the range of temporal variability you can get among the 50 members. So even the intensity of the variability strongly depends on the small perturbation you have at the beginning. The ensemble average is here. That's a total variability that you can split into intrinsic and forced, or chaotic and forced. And as you can see here, both are the same, have the same strength, which is not negligible. Half of the variance is actually paced by the atmosphere, the other one has random phase. So let's look further north. You have here the same scale, variance, STD, and latitude. And as you can see clearly, the forced variability clearly exceeds its intrinsic counterpart. Except here, where both, as we said, are equal, basically equal. And you have, this is the ratio between the intrinsic STD and the forced STD. And you can see there are secondary maxima here, and at rapid, the ratio is about 45%, because the forced variability has decreased and the intrinsic variability has maximum. How about scales, time scales? What you can see here on the middle is the spectrum. So you have latitude and you have a spectrum for each latitude between about 2 months and 28 years. Here you've got the forced spectrum, if you wish, and the intrinsic spectrum. If we start to the north, we have a strong decadal variability over there. Then there is some kind of a local minimum here, but picking up a maximum in the intrinsic variability back to a strong forced maximum at higher frequency and a decrease down, to the south. But there is an increase here. Maybe to summarize this, we can look at the contours, which represent isolines of R. this ratio between the intrinsic STD and the forced STD. You can pick the one you want. Let's look at the thick black line here. There, the chaotic variability exceeds the forced variability. So that's the case typically along the Gulf Stream latitude, and it goes up to 5 years here. And you also have a strong dominance of the intrinsic variability along the southern end. You can pick the 50% ISO line, and you see that over south of where I am here, you have the intrinsic variability representing at least half of the forced variability. So it's a complex signal, and depending on the frequency and where you are, you may or may not ignore this out of phase or random signal. How do Hofmüllers look like? On the left, you have the ensemble mean, Hofmüller, latitude, time, AMOC, interannual AMOC variability. You see some strong anomalies over there, which have been studied on the minimum there. And on the right, you've got a realization, this is number one, I think, of the intrinsic variability itself. You see, apparently, southern intensification, as we saw on the variance plot, and strongly coherent meridional signals. To look at this in more detail, we can compute the EOFs of these two signals. Let's focus on the dominant forced signal. It's 42% of the variance, and you have a negative pole, it's a dipole, negative pole, positive pole, which is well known. But this one is less well known. This is the dominant mode of the interannual intrinsic variability, which is one-sided, which represents 43% of the variance and which reaches its maximum at the southern end of the basin. And you have a secondary mode here, which reaches its maximum very close to the rapid array. So maximum of this mode at Samba, maximum of that mode at rapid. We did another ensemble simulation, and I just want to show you one result. This ensemble simulation was regional. So it was just the North Atlantic with a boundary, southern boundary at 20 south, where the intrinsic variability was 0. And in fact, you see that in this case, the dominant mode resembles quite a bit the second mode here. In other words, this leading EOF, which is very strong in the south, has just disappeared, suggesting that the main AMOC intrinsic variability source lies south of 20 south. And this is consistent with an unpublished study done by a master student. She looked at the advective heat transport multiscale variability, splitting it into forced and chaotic. And what I show here, so she computed that along those long transects across the globe. And this is a chaotic part of the total variance of this heat transport for different timescales. So I won't get into all the details. You see here that the values are pretty modest over most of the northern hemisphere, but they become quite big in this southern sector of the Southern Ocean. And actually, correlation studies and everything show that over these 3 ranges of timescale, the chaotic variance is about 1/2 of the total for heat transport as well. And they are well correlated with what's going on here. So the Agulhas current, the Agulhas system might be the main source of chaotic intrinsic variability for the AMOC and heat transport. So it's time to conclude. Over the range of timescale that the ensemble run can help us look at. The variability of the AMOC is partly paced by the atmosphere. This is what we may call the signal. But it's also partly chaotic intrinsic, if you wish. And this is a noise that may limit the potential predictability. The ratio of STD between this noise and the signal at interannual timescale is about not far from 50% at rapid and 100 at Samba. So again, it might be interesting to keep that in mind when trying to attribute what is being seen in time series. In other words, the atmospheric variability does not drive all observed AMOC anomalies. So the main source of this noise is presumably in the Agulhas system. This is pretty probable. And in fact, these results are consistent, and some of them complement other studies which have used, and this is, I think, important, different models, different resolutions, different setups, and these studies are compatible with ours. I just want to conclude telling you that if anyone is interested in these outputs, these ensemble outputs for AMOC studies or anything else, please let me know. And I thank you very much for your attention.
Questions? Gökhan has his hand raised again.
Thank you. So this is Gökhan Thierry. So I had a question about the noise part. Presumably you indicate that it's coming from the Ogulha system, but your model resolution is quarter degree, which is not really eddy permitting, which is in between the parameterized and not permitting regime. And what are the, I guess, roles of, I don't know whether you are resolving any mesoscale eddies, and whether noise is being imparted through that, and what would be the role of absolute versus relative winds that you use to force the system at the quarter degree resolution?
Well, indeed, our eddies are quite, weaker than observed in this at this resolution, but we have eddies. Animations are clear. I didn't take any today, but animations are clear. Just showing you this result from the paper by Sandy Gregorio a few years ago, I think we would agree that at 1/12 of a degree, we represent better the eddies. They are stronger, that's clear. But here are the results for the meridional structure of the forced, the total AMOC variance. So in black, you've got the 1/4 of a degree result, and in cyan or in pink, you've got the 1/12 of a degree. So the force variabilities are not that different, and the intrinsic variabilities as well. The ratios that I was showing kind of differ. We have two realizations of the 1/12 degree. So to make it short, qualitatively for the AMOC, the 1/4 of a degree model represents, I think, decently what's going on at 1/12 of a degree. So I'm not sure I got very well your question about absolute and relative.
We can discuss, that's okay. We can discuss that later. That's okay.
Jenny, up there.
Thank you. Hi, Dan Amran from NCAR. I was wondering if the connections between the atmosphere and the ocean, and thereby the forced part of the signal, could be greater in a coupled model, where there would be more feedbacks, especially in the longer timescales.
Yeah, the answer to that is, of course, this is a good question. The answer is not easy. I usually think that in order to split the ocean variability into forced and intrinsic, we had to prescribe the atmospheric variability. I don't know any easy way to proceed and to do that in a fully coupled run. Now, it's important to think about the limitations of those results, which are, again, quite robust across a range of models. To me, I don't know how to answer your question, but to me, an important question as well is to, I could talk for minutes about that, but what is the impact of this intrinsic variability in the atmosphere in a coupled run? I think those results strongly suggest that there is an intrinsic stuff, and which is even larger on ocean heat content, for instance, which might impact the atmosphere. And to me, that's an important question. Last thing, I could tell you why, but I think we underestimate, at least for surface field, the intrinsic variability because of the forcing strategy. We've done another ensemble, regional, which liberates the intrinsic variability at the surface. And in that case, we let the SST intrinsic variability, just be how we forced the ensemble, we let it develop, although it's damped in this occiput run. So I didn't directly answer you because I don't know the answer, but these are the things that your question made me think about.
Great, thank you.
All right, it's 11:30. I think we move on to the next talk. It's by Wei Lu. He's going to talk about deciphering climate impacts of a weakened Atlantic on overturning circulation during the 21st century.
Thank you very much. Can you hear me and see me?
Yep, we see you.
Okay.
Hear you.
Okay. I have a problem. Share my screen. Is go to the system preference. Okay. So could you please possibly open the PowerPoint and upload there?
Yep, I can share the screen for you.
Thank you very much, Jenny.
Might take me a minute. All right, do you see that?
Yes, great. Thank you. All right. So hello, everyone. I'm Wei Liu from UC Riverside. Today, I'm going to talk about deciphering the climate impacts of a weakened Atlantic meridional overturning circulation during the 21st century. So this work, I collaborate with Alexei Feder from Yale, Shenping Xie from Scripps, Shineng Hu from Duke, and my student Xianglin Ren at UCR. And this work is supported by NSF, my Sloan Fellowship, and Hillman Fellowship. Next slide, please. So first, let's look at the AMOC observation. So far, we have more than 1 decade observation in North Atlantic 26.5, the rapid array observation. So from this observation, we can see a decline of AMOC, but maybe it's due to the relative short time for this period. So there could be uncertainty for this decline, and at least it could be contributed by the multi-decadal AMOC variability. On the other hand, climate models, either from the IPCC AR5 or AR6 models, 2 generations, we can see an AMOC decline under the RCP 8.5 or SSP 585 scenario in the 21st century. So the scientific question is that, what is the role of the AMOC in future climate change? So to solve this scientific question, there are some problems because under anthropogenic warming, this AMOC slowdown occurs along with variations of other parts of the climate system. So therefore, within a fully coupled climate system, it is difficult to separate the effects of AMOC slowdown on climate from the effects of many other varying and interacting climate components. Next slide, please. So to address the scientific question, we use CCSM4. Basically, we use CCSM4 historical and RCP 8.5 scenario, 5 ensemble members. So you can see on the top right panel, and these 5 members show AMOC slowdown since 1980s. So basically, if we follow this RCP scenario, and we can see the ensemble mean showing as a thick curve, and shading with ensemble average, for the shading for the ensemble spread. So on the other hand, we conducted parallel sensitivity experiment with CCSM4. So based on the CCSM4 historical and RCP simulations, we extract fresh water from the subpolar North Atlantic, as shown in the blue shading on the top left panel. So then we redistribute the extracted fresh water evenly on the other part of the global oceans. So this sensitivity experiment, we have 5 members. So it follows the historical and RCP forcing. So the difference by doing this, could you please click? So by doing this, and we can maintain the AMOC strength through the 21st century under the RCP 8.5 forcing. So click, please. Then we compare the climate change during 2 periods. One period is 1951 to 80, which is the time before AMOC slowed down, and the other period is about 100 years later. So we calculate the difference between these 2 periods to infer the climate change, and also we compare the changes between our original simulation and the sensitivity experiments to extract the impacts of AMOC. So next slide, please. So first, let's look at the surface temperature change. The top left indicates the surface temperature change with a weakened AMOC, top right with a fixed AMOC, and the bottom one shows the difference between the two, which indicates the impact of a weakened AMOC. So we can find with a weakened AMOC in the default historical and RCP forcing simulation, we can see a very robust warming hole, North Atlantic warming hole to the south of Greenland. So this is common in many other climate models. However, if we fix AMOC strengths, and we can see the disappearance of this North Atlantic warming hole, and the difference shows that a weakened AMOC have an impact for surface temperature in form of a so-called bipolar seesaw pattern with cooling in the northern hemisphere but general warming in the southern hemisphere. The strongest warming occurs to the south of Greenland. So by doing this, CCSM4 experiment show that the weakened AMOC preliminary accounts for the North Atlantic warming hole in the 21st century. Next slide, please. So then we look at the physical mechanism, and we found that the cooling does not only appear at the surface, but also extend to subsurface. So then we conducted a heat budget analysis on a full depth water column between 48 and 50 degrees north in the Atlantic. So here the equation shows this budget, and the tendency term is on the left. On the right is balanced by the surface heat flux, the net ocean heat transport, meridional ocean heat transport, and diffusion term. So the net meridional ocean heat transport can be calculated at the difference between the southern and northern boundaries. So on the right bottom, I show this chart, which illustrates the numbers for all these different terms. But to summarize, we can see the main budget terms would come from the ocean heat transport as the southern boundary at 48 degrees north. So due to a weakened AMOC, it's caused anomalous southward ocean heat transport. Then it's caused a heat divergence in this region. So this net heat divergence caused the cooling for this column. And interestingly, we can see for the surface heat flux actually is positive, which means a weakened AMOC induced enhanced ocean heat uptake in the subpolar North Atlantic. Next slide, please. Then we look at the rainfall projection. And again, we can see the weakened AMOC, fixed AMOC, and the difference between the two indicates the AMOC impacts. So from this result, we can see the weakened AMOC caused a reduced rainfall over the North Atlantic warming hole, if you look at the bottom panel. And also, we can see a southward shift of the ITCZ, but note here, this ITCZ shift is not the leading mode for the tropical precipitation projection. So the leading mode still like the wet get wetter, dry get drier mode. Next slide, please. So how to understand this ITCZ shift? We use the atmosphere energetic framework. So the top panel shows the weakened AMOC case for the TOA flux and the surface flux change. Middle shows the fixed AMOC, and the bottom shows the difference between the two. So if we compare these panels, we can see basically the TOA flux does not have too much difference with weakened and fixed AMOC cases. However, the main difference comes from the surface. So the weakened AMOC causes enhanced ocean heat uptake, primarily with turbulent heat fluxes in the subpolar North Atlantic. Therefore, this drives a northward cross-equatorial atmosphere energy transport, which explains the southward ITCZ shift. And also, I'd like to mention the enhanced ocean heat uptake acts to dampen the anomalous sea surface temperature cooling in the North Atlantic. So this is the negative feedback. Next slide, please. Then next, we look at the change for the Arctic sea ice, basically the summertime. So we have two groups of curve. So the green curve shows the weakened AMOC case, while the purple curve shows the fixed AMOC case. So if we follow the weakened AMOC case, we can see Arctic sea ice will disappear during like the 2070s. So if we use threshold like the 1 million square kilometer for the ice-free condition. On the other hand, if we fix the AMOC, then we can expect larger heat transport into the Arctic. So correspondingly, we can see this Arctic sea ice-free time will be much earlier, so 6 years earlier. So to summarize, the AMOC impacts cause the summer Arctic sea ice-free time. Basically, if we have a weakened AMOC, we will see a delay about 6 years. Next slide, please. And we also look at the AMOC impacts in atmosphere. So the top panel shows the annual mean, lunar mean atmosphere temperature change. And the bottom panel shows the boreal winter time, DGF, lunar mean westerly wind change. So if we look at the difference between the two cases, we can see the weakened AMOC cause a cooling in the northern hemisphere, extending from the subpolar region, polar region, to the high latitude in the tropical region. And correspondingly, during the boreal winter, we can see a shift of the northern hemisphere westerly wind polarward. So that's for the atmosphere. Next slide, please. So finally, we look at AMOC impacts on global marine heat waves. So we look at two periods. The top panel shows the past 4 decades, and the bottom panel shows the end of current century. So from the left to right, we are looking at the duration, annual frequency, and intensity change for the marine heat waves. So we found that, oh, by the way, the dotted area shows the significance was not, the dotted area shows the difference was not, is not significant. So if we look at the top panels, we can see during the past 4 decades, the AMOC impacts only significant in the North Atlantic warming hole region. However, if we look at later time, by the end of current century, we can see the AMOC impacts will become more and more significant, which covers much area of the North Pacific, North Atlantic, even Arctic. So especially if we look at the frequency, and we can see even like the positive change for the AMOC impacts. So that is because in the North Atlantic warming hole region, the duration will be ultra long, so very, very long. Therefore, within a year, and maybe we can only see 1 or 2 marine heat waves. Therefore, we can see this anomalous change for the frequency. So to summarize, the North Atlantic warming hole region will reach a near permanent marine heat wave state by the end of current century without a slowdown of the AMOC. Next slide, please. So here is our conclusion. First, we look at the slowdown of AMOC impacts on the surface temperature. We can see the AMOC slowdown causes North Atlantic warming hole in future climate, along with the local reduced rainfall and enhanced ocean heat uptake. And also the weakened AMOC can cause a delay of ice-free time over the Arctic during the summer for 6 years. And in the atmosphere, we can see a weakened AMOC can shift the northern hemisphere mid-latitude jets polarward. And for the marine heat waves, and basically the AMOC impacts were not significant in general for the past 4 decades, except the North Atlantic warming hole region. However, in later of current century, the North Atlantic hole warming region will reach a near permanent marine heat wave state without a slowdown of the AMOC. So next slide, please. So thank you very much for your attention, and more details can be found in these 2 papers. Thank you.
Thank you. Any questions? All right, I do see a question. Let me go up.
Hi, Wei. This is Chris Paikush from Woods Hole. Thank you. That was an excellent talk. I have a question about your ocean heat content budget. So if I understood you correctly, you showed that heat content over the warming hole region, that what you're seeing is a heat transport divergence that's being partly compensated by changes in surface heat fluxes, and the net result, your TEN term, was a cooling. that tendency, it's a really small residual of two much larger competing terms, the heat transport divergence and the heat flux. What determines that residual? You know, why isn't it that the surface fluxes completely compensate for the ocean heat transport divergence and you get no change in storage? What's determining that storage term since it's so small relative to the two other terms?
Thank you very much. That's a very nice question. Jen, could you please go to the slide for the heat budget? All right. The previous one. Thank you. Yes, thanks for the question. And yeah, we conducted these heat budgets based on the CCN4 model outpost. Basically, we have all the terms for the heat flux and also net ocean heat transport and diffusion. And of course, you may notice more details regarding the eddies, and also we also decompose to the ozonal corresponding to the gyre part, and also the overturning corresponding to the AMOC part. So from this chart on the left, we can see, yeah, the tendency is smaller than the heat flux term and also the divergence term of heat transport. So, but it was not that small, because basically you can see it's about 1/3 of the net heat transport. So yeah, so basically the physical understanding for this one is that the divergence of heat transport due to AMOC slowdown basically kind of like the largest term. So it's caused the cooling for this water column, but it's partially compensated by the surface heat flux, ocean heat uptake. But this compensation is not enough. So still we can see the net cooling from this compensation still contribute to this tendency, the negative number. Thanks.
Okay, we've got an online question from Martha Buckley.
Hi, thanks for your talk. I was going to point out that I think your results are sort of very consistent with a lot of the literature on water hosing studies. In some sense, you're almost doing a reverse water hosing, right? So instead of imposing fresh water, the climate system, because of warming, is causing the AMOC to decline, and you're adding the fresh water to reduce that decline and maintain the AMOC. But this sort of assumes that that fresh water that you're putting in has sort of no other impact, because you're saying that, you know, the differences that you find are basically due to the AMOC decline. So, I mean, your results seem very consistent with the prior literature around the warming hole, for example, that, you know, the ocean converges heat and that causes more heat uptake. So John Marshall wrote some studies about this. So I don't think that, I'm not like saying that the results are not valid, but you do have to remember that you are putting a perturbation in the system, and that's not sort of this, it's not necessarily the same as sort of, you know, if you hadn't put a perturbation, sort of trying to untangle things in the coupled climate system like you were talking about at the beginning. Because, you know, you say, well, okay, in the problem with the coupled models is one thing adjusts and another thing adjusts as well, right? So if the AMOC declines, maybe the gyre circulation, you know, compensates. So, you know, I just think you have to be careful that, you know, whether this is exactly what's happening in the coupled system, because you have imposed something, right?
Yeah, thank you very much. This is a very nice question. And yeah, I agree. Basically, what we did, you can call reverse hosting or dehosting. And two things here. First, we do that carefully. Basically, you know, can do hosting for any magnitude, but how much hosting will be nicely to even this AMOC slow down. So that would be the first thing. So we need exact or nice magnitude. The second would be, what would be points for doing this perturbation experiment? You are right. So it's a coupled system, right? So anything you do, you perturb, it will change the coupling or it will break something. But the point here we are doing for the reverse hosting or dehosting is that we want to conserve the heat flux, the heat energy budget, the first thing. And the second thing, and we want to allow the natural interaction between the ocean and the atmosphere. So as you can see from the analysis, first we use energy budget analysis for the atmosphere energetics. So if we can perturb other heat flux or winds, and basically, it's not be a nice idea to conserve energy. And also, if we perturb the hosting, we just change the salinity, that's true. But from the atmosphere, and the atmosphere can easily feel the change for the sea surface temperature, but for salinity, it's a different scenario. So by doing this, and we are allowing the natural interaction between the ocean and atmosphere, so you can freely diagnose the change of turbulent heat flux, and also you can even look at the response of the winds, because the winds can change, but that's due to the change of the AMOC, not through the heat flux, but through the fresh water. So that's basically the point for this one. Thank you.
Yeah, thank you.
I have a hopefully not too technical question, but maybe I missed this in the beginning. How do you fix AMOC? I mean, as a traditional language, that's a zonal integral either in depth or density space of velocity, but of course it's tied to geostrophy and the density field. And so how do you fix that, yet allow SST to vary? It seems like that's part of the AMOC signal.
Thank you. Yeah, that's a very nice, good question. Yeah, that's true. We use the maximum of the stream function in the North Atlantic, basically the common metric to define the AMOC strength. So we use this to keep the strength more or less constant through the 21st century. But you are right, the AMOC system is complex. So on different coordinates and also regarding the structure, there could be some difference even we are using this dehosing method. So basically, we first do the hosting to find the relationship between the AMOC strength and the hosting or dehosting we put. And then based on this relationship, and we can design our experiment scheme and finally reach to our experiments to fix the AMOC strength during the 21st century.
Okay, one more question.
Thanks. I'm Jamie Palter from the University of Rhode Island, and I really enjoyed learning about this ensemble of experiments. When I talk or teach about AMOC, the question I most frequently get is, how will our weather change, and will there actually be places that are colder? And my typical response, previously uninformed by this kind of work, was that if we warm enough to shut the AMOC, then we warm probably everywhere, even despite the AMOC slowing or and I think that's true in your first set of slides that showed warming everywhere, even though reduced warming under AMOC. But I wonder if there's any seasons or like small locations that I couldn't make out that are actually colder than today under the reduced AMOC, even in RCP 8.5. And maybe even more importantly, there's been work that shows when the ocean heat transport slows down, the atmosphere compensates by doing more meridional heat transport, and that happens through storminess in the mid-latitude jet. So are there places that are stormier or colder under RCP 8.5 reduced AMOC than they would have been without the reduced AMOC? Thanks.
Yeah, thank you very much. That's a very nice question. And for the first part, my understanding is that the warming hole in future climate basically is kind of competition. It's kind of like competing effects between the anthropogenic warming and the AMOC cooling due to the slowdown. So it's like if the many models show the strong warming, and but I had a paper like a couple of years ago. If we have a double CO2 experiment with AMOC collapse, that's true, and we can see a cooling, a very large cooling over the North Atlantic, subpolar North Atlantic. So that means in that case, the AMOC slowdown induced cooling is much larger than the cooling due to the double CO2. So that's the first part. And the second part, yes, I totally agree. And there would be the compensation between the heat transport in the atmosphere and the ocean. So we look at the atmosphere, but we'll look at more details for the compensation part. Thank you.
Okay, I think we'll move on to the discussion. Let's thank all of our speakers from the morning. Okay, so we've got until 12:30 for open discussion. recall that the theme of this session is mechanisms and predictability. So we can revisit the talks from the morning, but keep in mind that one of the purposes of the meeting is looking forward, big questions, what comes next, and that sort of thing. So I'd like to hear some discussion on, let's start with mechanisms. What do people think are the big mechanisms that we do not understand very well? So I take it everyone understands everything.
I certainly don't. So this is a question to your point, Mike. I'm going to direct it at Thierry, if he's still on.
I'm here.
Yeah. Hi, Thierry. Chris Pikers from WHOI. Curious, so two questions. One's a little bit technical, but I think is important, and the other is for you and Jiayan, all about mechanisms. So when you run your models, are you specifying the atmospheric state or fluxes? And if you are using a bulk formula model, do you have a sense of the relative importance of anomalous surface fluxes versus sort of spontaneously sort of generated internal ocean instabilities on what you're seeing?
So this relates to the short answer I gave before. In this big, in the global ensemble I talked about, all the members are driven independently through bulk formulae. Okay, and as we know, SST is implicitly relaxed to an equivalent temperature within each member. So the SST spread is, let's say, artificially damped. It's limited. But if you look below, the spread of temperature increases downwards, down to the depth of the thermocline, typically. We thought about it after the run, but we did a sensitivity experiment using the regional ensemble. And so we did the regional ensemble just like the global, and then we did another one where we apply on all members the exact same RC fluxes. We actually ensemble average the RC fluxes at each time step. So each member has its own, computes its own RC fluxes. And then we ensemble average and apply them all the same to all the members. In this second case, the spread that was like this in the first case, so some kind of substantial spread at the depth of the thermocline that was decreasing upwards, remained roughly constant between the thermocline depth and didn't change between the two ensembles. So the spread of temperature at the thermocline was the same, generated by the same internal dynamics, if you wish, but would remain the same up to the surface. And to me, this is consistent, physically more consistent with the fact that, let's say, multiple scale intrinsic variability is not likely to be damped, I think, by the atmospheric forcing in a coupled run. The atmosphere is more driven by, let's say, interannual and longer frequency variability than the opposite. So in this second run, the forced variability was still behaving the same, if you wish, but we liberated the SST spread. So that was the second part of your question, and I'm sorry I forgot about the first part.
So I only asked one question. Thank you, that was really helpful. So the second question is for you and Jiayan. So after I ask it, I'll give the mic to Jiayan. So Jiayan is not here right now. Maybe I'll open to anybody. So we saw Jiayan's talk talking about sort of adiabatic wind-driven variability, and it was really remarkable how well that explained what we see, for example, at Rapid. And now we're hearing Thierry tell us about how important at a place like Rapid the intrinsic variability is. So I'm wondering where buoyancy forcing is in all this, if we can explain everything from intrinsic variability and wind driving at Rapid. I'm being a little bit cheeky, but yeah, I'm curious what people think, interpreting Thierry's results and also Jiayan's results, what role buoyancy forcing has on the timescales that we're resolving here, or what implications these results have for our understanding of the role of buoyancy forcing.
maybe I can start with, actually, John, this earlier mentioned the paper by Agathe Zhang, or Jeremy, as you say in English, which I had heard of, but I just have a look to it. And I think their paper, using a small ensemble of 112-degree model simulations, provides some interesting answers to your question. They actually split the AMOC variability into geostrophic, Ekman, and all that stuff. I mean, Florida current transport. And they give some information about the intrinsic versus forced nature of these components' variabilities. So I just discovered the paper. I don't remember the answer, but I guess you might find some elements in this paper. I don't have the answer because we didn't split AMOC variability into buoyancy forced component and wind forced component, but they did.
I think part of the answer is that those latitudes and timescales, buoyancy forcing isn't very important. Fans of buoyancy forcing might not like that, but that's what the evidence is. And I'm a fan of buoyancy forcing, but also have gotten interested in the wind forcing. But there's an indirect role of buoyancy forcing in that it sets the stratification, which sets the baroclinic deformation radius and the wave speeds, right? So it's kind of buried in the adiabatic models, not explicitly represented. And Susan?
Yeah, although you were trying to discourage me from talking earlier, Mike. So
No.
Since you spoke up, I'm coming in here. So also a fan of buoyancy forcing. I actually think it's helpful to shift the discussion in a way to talk about local and remote forcing. And so I think in the subpolar gyre, subtropical gyre, clearly we're seeing very strong impact of local forcing, right? But I'm not sure that we can rule out buoyancy forcing in the subpolar, North Atlantic. But the question that I've often posed in my presentations is that those anomalies, the downstream evidence for those in the observations is really lacking. There's a very large recirculation timescale in the subpolar North Atlantic. And there's papers on this, it could take decades for those anomalies to get down. Like we've moved away from the idea that a volume anomaly is formed and then it coherently moves downstream, right? Either by interior pathways or by the deep western boundary current. And Tom mentioned yesterday that more than 2/3 of that Labrador seawater that's formed stays in the subpolar North Atlantic. So we really, I think this whole notion of when we're looking at these density anomalies that are responsible for the AMOC, appreciate the conversation about, intrinsic and wind-driven variability, but I also just think the local and remote is very interesting as well. So we see buoyancy-driven, AMOC variability in the subpolar North Atlantic on our observational timescales.
I need to clarify. I didn't tell Susan not to speak up.
Kind of did, Mike.
But what I did say is that I want to encourage some of the younger people here to speak up. Now, as someone who's virtually the same age as you, yes, that's what I'm saying. No, seriously, part of the purpose of this meeting is looking forward, and I want to hear about the ideas from people that are going to be running the future programs, in addition to the ideas of people that have been running the programs in the past. So, Gokhan, Susan, let's hear some complementary ideas from some of our younger participants.
Can I follow up what Susan said?
Absolutely.
Yeah. This is Jiayan from WHOI. So I just want to follow up what Susan said. I mean, it's very difficult to separate buoyancy forcing and wind stress forcing. I mean, the buoyancy forcing really play multiple roles. One is in terms of deep water formation. There is a production part. The other one is changing the thermal wind, then changing the circulation. So my view is that for short time scale, and as Susan said, I mean, I think Susan was referring to Tom Rusby, that deep water formation might be in overproduction capacities. There's tons of water in the Nordic Sea and the subpolar basin. So for the shorter time scale, the variability is not the production. And there are a lot of stuff in the inventory, but it's the transport. I mean, it's is the transport mechanism, how those water being removed. I mean, if they are not effectively removed, then next year, sure, you still have the production, or you might even shut down the production for a year, but there's still tons of water in your warehouse. But that relates to the question is what is regulating the transport mechanism? And that would be wind stress change is one of them. I mean, you move water convergence and divergence across latitude. But also change of deep water formation side matters. I mean, you can imagine that if the water is formed in the interior subpolar gyre, away from major topographies, then you tend to create a close, PV contours, and the water just happily recirculating without bothering low latitude. As compared with if the production is moved, say, to the Iceland basin near the mid-ocean ridge, then you suddenly open up another highways, allow what I said yesterday, the 18-wheel truck transporting the deep water southward or to the western boundaries. So I think those are the issues that not really separate, but buoyancy force play multiple role. I mean, not just the production, but also changing the circulation, and changing the circulation can change the export.
Yeah. So that all good points. So maybe we can discuss a little around that framework of mechanisms that we don't understand very well, the spread of convective water masses, both longitudinally and latitudinally. So what would we need to observe to help understand that, aside from the distribution of the waters? That's kind of descriptive. And what would we diagnose in models to understand that sort of behavior? Thoughts? Tom?
What's the cutoff age?
You've looped around to the beginning again, Tom. So are you volunteering to run the next program? Is that what I understand?
Brought this up with yeah. I'm not sure I caught all the details here earlier, but I'd like to repeat what I said yesterday, that when we have high NAOs, we have plenty of production of intermediate water down to order 2-kilometer depths. And these waters spread out primarily to the east. When we have low NAO periods, such as in the 60s, and we don't produce those waters, but we still have, I assume, roughly the same amount of waters coming around Greenland. I don't know that that flux changes that much. In any event, the waters leaving the Labrador Sea go south along the escarpment and fill the Slope Sea. And it's a huge difference. I have the same amount of water roughly going into the Lab Seas, and during low NAO periods, I'm shipping the water south. And during high NAO periods, I tend to ship it to the east at greater depths. How does that look? First of all, what is the mechanism? What is the mechanism? I don't know that we know that mechanism. That's a rather simple question, I think, and should be amenable to fairly simple models to sort that out, because it has a big impact, I think, on how you appreciate the MAO change. If you ship the water south and it's shallower, I don't know. It looks like I'm having more water going south rather than zonal, but maybe it's not as dense, and maybe it shows up as slightly weaker AMOC. Whereas if I put it into the deeper layer, even though it goes east, I still have to ship water south. It looks like a stronger AMOC. So the Labrador Sea may, in overturning terms, not look like a big player. We know the Erminger Sea is a bigger player in that sense. But it plays a key role somehow, or it is an important player in this mechanism by which way I where I send the waters that I have transformed. So that's a challenge to the modelers, I guess. It's probably a challenge to us observers as well, how we can improve our ability to sort that out. I'm sorry I took so much time.
let me ask then of the modelers, have you looked at this kind of decadal variability in the spread of North Atlantic deep water? I know Susan's done a lot of work on shorter, perhaps shorter time scales. I don't know if you've looked at these kind of decadal time scales.
Yeah, I think Sajia Zhao is on the call. Maybe this is really her work when she was a PhD student with me, and there's a paper called Break-Even Linkage Between Labrador Seawater Production and Its Export to the Subtropics in a modeling framework over many decades. And basically, you see that from year to year, you cannot track the variability of Labrador seawater you're forming in the Labrador Basin with what is exported downstream. There's no relationship, because a lot of that Labrador seawater, like I just mentioned, is recirculating. There's a lot stored here. And so you just, I know there have been attempts to track that down the deep western boundary current. You may be able to do it with TNS signatures, but there's not the volume that's produced in the Labrador Sea is not related to the volume that is exported, from year to year or even on longer time scales. So that question actually that Tom's asking was one that was motivated by the float program that Amy and I ran many years ago, XPath, seeing that about 2/3 of the waters that are coming out of the Labrador are recirculated. And we were saying, what determines the fraction of waters that are exported and the fraction of waters that are recirculated? And this gets to some of Martha Buckley's work in terms of transitional latitudes. There's another name for it, between transition zone. The dynamics there, I think it's still open whether or not this is wind-driven dynamics or eddy dynamics that's really regulating that volume of water that's exported. But very, very interesting, yet unresolved, but there are some things in Sajia's paper from 2015 or 2016 that sort of set up that problem that you have posed, Tom. Don't hand me the mic again.
Yeah, how do we do that? This monitor isn't done.
Alexei, do you have a comment?
Yes, Alexei Fedorov. So just continuing this topic. So interaction between these different regions. We have this modeling simulations where we looked at the response of a particular model, IPSL CM6, to the decline of Arctic sea ice. And the model actually quite reasonable, so it doesn't produce any deep water formation in the Labrador Sea, similar to the OSNAP array. And so what happens in the model with Arctic sea ice decline, there is a little bit of freshening, so AMOC starts reducing a little bit. But then there is a compensation. There is actually an activation of Labrador Sea convection, and AMOC recovers and stay roughly at the same level. So at least in these experiments, there is a compensation. As soon as you get a weakening of one region of deep water formation, there is a strengthening of deep water formation in the other region, where it was actually not even active before. So whether this compensation happens in reality, it's hard to say, but this compensation happens because this compensation happens in the model on multi-decadal timescales. So we're talking about something like a 50-year timescale. So at least there is this indication of this compensation and the sort of interaction between different regions that keep the AMOC more or less the same. Yeah, so just a comment on this.
Any more comments on this theme? All right, I'd like to talk a little bit about predictability then. It's kind of the other half of this task team. We didn't see as many predictability talks. Chris? Sure, go ahead.
So this is Chris Little in AER. So I just wanted to stay on the mechanisms theme for at least 1 second, and it might just be a function of my own lack of knowledge about it. But I think Thierry's point about the Agulhas variability driving AMOC, I wasn't sure. I'm not sure how much is out there in terms of the mechanisms at play there, and I think it plays into predictability too, because I think Thierry said that that would be something that would just introduce noise. But I mean, is there a propagation or some element of predictability, even given the fact that it's sort of an intrinsic signal that we could see?
Anybody want to respond?
Well, maybe I can risk an answer. To be frank, I've never really understood that the presence of intrinsic or chaotic variability in a system necessarily decreases predictability. If you initialize properly your state, I think you're not doomed. You can still predict for some time, especially if the chaotic signal has a low frequency, as we see there are some of them in the model. But the thing is, the Agulhas current, the Agulhas dynamics, which I show a few results, induces some random or variability over a wide range of scales. This one may be seen as a noisemaker. These are not published results, but it's been, as I said, the work of a master student. I would like to publish these results, but we have to dig into it a bit more. So it may not be a source of predictability for the Agulhas current, but it's not the case maybe for all modes of variability. I didn't show it, but there is a co-variability between the AMOC at rapid, the intrinsic AMOC variability at rapid, and some other indices, such as the volume of the subtropical mode water reservoir and other indices. You have some modes which are more regular, but still are out of phase among the members. So it's not an easy question, an easy answer, at least.
Fine.
Yeah, hi, this is Jamie Palter again. I think this question kind of might bridge the gap between what we're talking about now and the predictability piece, which is on multi-decadal timescales, and I hope I'm not putting you on the spot. This has to do with Steve Yeager's work. Just did a really nice piece of work with a very high resolution model showing that convection and buoyancy forcing in the Labrador Sea that leads to thicker Labrador seawater layer leads AMOC variability on decadal timescales, also providing some predictability. And I feel like we're kind of maybe have just been a little dismissive of that, of buoyancy forcing and Labrador seawater formation in variability, perhaps because we're looking on too short of timescales in the observational record, but on these multi-decadal timescales, it could play a role. I hope I'm not putting you on the spot, Steve, if you want to comment on that, and then also how it could produce predictability, because I find that really intriguing.
Yeah, I might have trouble taking notes while I'm also talking, but my take on these issues is that there's a bit of a disconnect in talking about mechanisms and variability and predictability, buoyancy forced or wind forced, because we're talking about a spectrum of timescales and phenomena. And in initialized prediction work, particularly decadal prediction, the North Atlantic predictability is coming from AMOC in a general sense that involves decadal variations in the strength of the subpolar gyre, as well as kind of the traditional overturning. And in the high resolution work that Jamie just mentioned, we find that what's happening is we get formation of Labrador seawater that varies on multi-decadal timescales. We get large variance in the thickness of Labrador seawater. And it doesn't, that Labrador seawater, in line with the observational work, doesn't necessarily get transported to the subtropics. It kind of flows eastward, as Tom has been mentioning. But what it does do is it induces steric effects on sea level height. And I think that's kind of the key missing link here, is that we're thinking about kind of overturning circulation, but the thing that matters to climate is the transport in the surface layer, and that's related to sea surface height gradients, geostrophic flow. And the way you get a predictable sea surface height gradient is from deep thickness anomalies. And once you initialize a coupled model with that thickness anomaly, it stays there. It's subducted. It's not going anywhere. And so it just gives long decadal memory to the coupled system by inducing gradients that then impact surface transport and SST. So we've seen that in our coarse resolution initialized prediction, and now we're starting to see it in high resolution. So I think this is a robust result.
So do I interpret that to mean the limitation of predictability is initial conditions?
Currently, then there's the question of, can you predict anomalous formation, which would extend the time window of predictability. Currently, there's little indication that we can predict anomalous formation, but we can initialize with anomalous thickness in the ocean, and that gives us decadal timescale predictability in the North Atlantic.
So intrinsic variability on those timescales is small?
Yes.
Aside from the formation, which might be intrinsic variability?
Yeah, so that relates to the poster that I have, and it relates to Thierry's talk as well. When we get to using eddy resolving ocean models, there is certainly more noise in the system. But if we reconstruct AMOC, or if we reconstruct deep thickness anomalies, we find that the signal to noise is actually quite high. So the eddies do introduce spread, but there's kind of robust NAO-related multi-decadal thickness anomalies that we see even in high-resolution models.
So, Martha, you have your hand raised?
Yeah, thanks. So I was going to comment a little bit about the predictability in the Labrador Sea. So from what I know of Steve's work, and also some work that Laurie Trenery and Tim DeSole and I have done, predictability is actually quite low in the Labrador Sea. So Steve Yeager's work showed that the Labrador Sea did not have high predictability even for the upper ocean density, but the central subpolar North Atlantic was predictable, as was the ocean heat transport at 50 degrees north and this Grand Banked gyre, basically. So some anomalies in this transition zone were predictable. And I think that, it's, so the predictable signal does not appear to be coming from the Labrador Sea, at least unless it's a signal that is isolated below the subsurface, right? So you could, maybe the SST isn't predictable, but there's some subsurface signal that is predictable and propagates elsewhere. But the place where SST is actually predictable is in the central subpolar gyre. And I think that it's possible that, the AMOC has something to do with this, because this is sort of the warming hole region. But another thing that causes predictability in that region is just reemergence. So if you simply take the SST anomalies and you calculate a seasonal autocorrelation function, it goes down in the summer and it comes back up in the winter. So that's a 1D process, right? A very simple 1D process that enhances predictability. So you can't say all the ocean predictability is related to the AMOC, although some of it may be. But the Labrador Sea isn't very predictable, at least at the surface.
So kind of connecting predictability themes with some of the talks that we heard earlier, hearing more and more about the connection between the Arctic and the subpolar gyre through the Nordic seas, and the importance perhaps of sea ice. So is predictability of sea ice going to be a limiting factor? I don't know that we have many people here that work with sea ice and sea ice models, but if anybody does, I'd like to kind of hear that perspective. How well are we doing on ability to predict sea ice? Because I think that's going to have large consequences for water mass transformation, circulation, AMOC, in particular, in light of the retreating sea ice edge on the western side of the Nordic seas. I think we're really changing the heat flux patterns, the convection patterns. You know, I think we're going to be convecting right into the boundary current instead of only in the middle of the gyre. So I'd like to hear any thoughts on that. Maybe we invited the wrong people. I don't know. Yeah, it could be the wrong question. That's all I got, though.
I can make a, this is Martha Buckley again. Can I make a comment on sea ice?
Yes, bail me out, please.
No, it is, so I'm not the right person to comment on this. And I don't know about, one would think that, you know, I think that biases in sea ice strongly impact predictability in the models that we have. So I looked at, so you asked about something different, right? More the variability, but the biases on a lot of models that are used for decadal prediction, there's a number of them that have an ice-covered Labrador Sea. And that just, it changes what the circulation is immensely. And what I found is those models that have an ice-covered Labrador Sea do not have this feature that of this central subpolar North Atlantic being highly predictable. So the places that are predictable is altered when you basically have a different mean state, which is not surprising, but yet when there's these CMIP multi-model initialized predictions experiments that, you know, they look at where is it predictable, where is SST predictable, some of those models that are ice covered in the Labrador Sea are included there. So, and they have a different climate. And you know, you would think that when you change the sea ice in the future, that will alter predictability, because there's places that are covered in ice and they no longer become, they no longer are covered in ice. So that's another feature of the sea ice.
So you commented earlier that Labrador Sea was not very predictable, and you know, we've heard various things about how much more important water mass transformation is to the east of the Labrador Sea than in the Labrador Sea. But you're suggesting, if I understand you correctly, that when the Labrador Sea is covered with ice, the interior of the subpolar gyre is predicted poorly. So is that because those models also get other things wrong, or is that because the Labrador Sea is important to the predictability in the middle of the gyre?
So I don't know if I can, I don't know the answer to that question. I think that, you know, I mean, it could be that those models are somehow biased. So, you know, if you think this predictability in the central subpolar gyre comes from the AMOC, well, those models could be, have too weak of an AMOC or something like that. And that could be, you know, affecting their predictability in that central subpolar gyre. I have more of an observation in the sense is if I look at the mean predictability amongst a group of models that have that are not ice covered in the Labrador Sea, you know, the ones I find most interesting in comparing to observations, those look one way, and the other ones are a bit all over the place, you know, but they have deep convection in the eastern portion of the gyre. So, you know, it's basically all in the Icelandic basin. So the climate of those models looks different, you know? So
yeah, maybe there are too many other things different.
Yeah.
We're coming close to lunch. Do we have any more comments? I see some hand in the back. Oh, well, they're pointing at each other, so that's not good.
Oh, that's okay. I can bring this up later. Thank you.
Okay, well, it's 12:30, so thank everybody, and we'll take a break for lunch.